Now, if we have a look at this example number 20, which is a case 2 example, it says there's a graph representing the growth of a population of bacteria P over T hours. So we're going to have an equation P in terms of T. The graph has a gradient of 0.6, so we know that if it was a y equals mx plus c equation, m would be 0.6. And it meets the vertical axis, so that's the y-axis essentially, at 0, 2. So we know that our y-intercept is 2. The scientists suggest that this growth can be modelled by the equation p equals a times b to the t. Write down an equation for the line. Well, we've got log p on this axis here, that's our y-axis, so we can have that as the subject of our formula. That is equal to, the gradient is 0.6, so it's 0.6 times t, and then our y-intercept is 2, so it is plus 2. Doing it in that way gives us a linear equation, so log p equals 0.6t plus 2. But we want to find the values of a and b, and that was where p, not log p, equals a, b to the t. To turn this log p into p, we have to do the reverse of what's happening. So this is log base 10 of p equals this stuff. That means that 10 to the power of this stuff is equal to p, and that's exactly what's happened here. P equals 10 to the power of this stuff on the right. Using index laws, we can multiply that out, or separate that out, I should say. So because it's an index plus another index, that becomes a multiplication of the same base with the two different indices. What we can then do is we can move the 10 squared to the front because multiplication is commutative, and that is 100. And then we've got 10 to the 0.6 to the t, because when we've got two powers multiplied together, we can take one outside of the brackets. So we end up with 10 squared, which is 100, times 3.98 to the t. In our original format of our equation, we had a times b to the t. So a will be whatever constant is just on its own, and b will be whatever constant has a power of t. So a is 100 because it's the constant on its own, and b is 3.98 because it's the constant with the power of t. So a is 100, b is 3.98. Last part of the question says interpret the meaning of the constant a in this model. If t were equal to 0, 3.98 would be equal, 3.98 to the 0 would be 1. So this equation, when t equals 0, i.e. when no time has passed yet, this equation equals 100. So the value of a, which is 100, gives the initial size of the bacteria population.